When you have more than one center of gravity, things can be easy or complicated, depends. But let's look at this guy. The driver of this truck was not very smart. He has 4 industrial refrigerators loaded on the back of his truck. So this is the rear view of the truck. The refrigerators are uniform, so that the center of mass of each is in the middle of each fridge. So these are the refrigerators. It's tied down with this little tie strap. And so what we're trying to say is, what happens? How steep of a hill can he safely drive along? And so he's driving sideways across the hill. What's going to happen is it could tip, and if it tips, it'll tip over this spot. It could slip, and if it slips, it'll all slip together. So let's analyze the tip over scenario first. All right. What I want to do is say, let's handle the refrigerators as one unit, and then the truck itself as another unit. So let's draw the centers of CG of each refrigerator right like that. It will have a mg sine theta and an mg cosine theta. Okay. The truck itself says that the truck weighs 8,000 pounds and its center of gravity is in the middle of the truck and 3 feet off the ground. So there is the center of gravity of the truck, and it will have an mg sine theta and its own mg cosine theta. All right. There's going to be a normal force and a force of friction. Okay. If I consider the tipping scenario first, what happens? We know that the normal force, let me just put it over here, it will tip about this point, and we'll call that point A, and B goes to 0. So B goes to 0 if it tips about A. How do we do that? Let's sum the moments about A. Sum the moments about A is equal to 0. See if we can find out some angle. Okay, so first of all, I have mg sine theta of the refrigerators times its lever arm. Let's see what the lever arm is. They're 6 feet tall, so half of that would be 3, and they're sitting 3 feet off the floor, so this would be a lever arm of 6. Okay. Let's also look at the cosine theta of the refrigerators. Minus mg cos theta of the refrigerators, and the lever arm, here's mg cosine theta. The lever arm is going to be this. You can see that they're 2.5 feet wide, so half of it would be 1.25, but they're 1 foot from the edge of the tire, so that would be total of 2.25. Okay, there's the refrigerators. Refridge. Okay, now let's consider the truck. I'm going to consider plus mg sine theta of the truck, and its lever arm is just this 3. And then minus mg cosine theta of the truck, and the truck's lever arm for that would be half the total width. And it looks like the total width is 7, so half of that would be 3.5. And there we go, the truck. Equals 0. Okay. How much do we have? The mg's of the refrigerators are 1,000 pounds. So I'm going to say that's 1,000 sine theta times 6. Actually, there are 4 of them, so I'm going to say that those are 4,000 pounds minus 4,000 cos theta times 2.25. The truck itself weighs 8,000 pounds, so plus 8,000 sine theta times 3 minus 8,000 cosine theta times 3.5 is equal to 0. Then you just start combining and you get a little arithmetic and you get sine theta over cosine theta is equal to 36,600 over 48,000. Now I'll let you do the arithmetic there. But sine over cosine is equal to tangent. And so you can solve that for the angle. Theta is equal to 37.3 degrees. And that'll be the angle that it tips, which is an important kind of consideration. Okay, how about slip? What is the angle at which it will begin to slip? So again, this is sideways, so we don't really care about the difference. I mean, the coefficients of friction of both tires are going to be the same. And so here we can use the slip angle, the phi, if we wish. So I'm just going to say phi is equal to the inverse tan of mu. In this case, it says that it is 0.7, so inverse tan of 0.7. And I got phi here. Theta, or phi, at which it begins to slip, is going to be equal to 34.9 degrees. So in this case, it will slip before it tips. Even with the coefficient of friction of 0.7, which is pretty high, it will still slip before tipping here. So it's actually, this truck is actually a little more stable than I would have thought by looking at it. It looked to me like it might have a tendency to tip first, but when we analyze it, it actually slips first. All right, the last one I want to consider in this particular section is this loader, which has a weight. It's actually a stone in its front bucket, and he's going to tiptoe slowly down this hill. And you can kind of see what's going on as he moves forward. He'll be down the hill, and we want to find out what the steepest hill he can go down. All right, how do we set this up? Let's draw the Freebody diagram on the hill and see what we can find. So I'm just going to extend the hill like this. I'm going to draw the loader, something like this. Well, that's not a very good loader, but he's got a stone sticking out, and I'll say that there's a bucket that looks like that there. I hope that that's good enough for you. Let's draw the forces as we see them. It's got an mg here, and there's another mg here. And this is going to be mg sine theta of the rock. This is mg cosine theta of the load or the rock. There's also an mg cosine theta of the loader, the tractor, and then there's mg sine theta like that. In this case, we're not talking about tipping, so this is we're not talking about slipping. We're going to assume there's enough friction to keep it from slipping down the hill. So this is only a tipping scenario. So in this case, we have A and B, and in this case, B goes to 0. There's a force of friction that looks like that. So again, in tipping scenarios, just sum the moments about the point of rotation. In this case, it would rotate about point A. So I'm just going to do that. Sum of the moments about A is equal to 0. What have I got? For the stone, I have an mg sine theta, and it has a lever arm of this right here, which would be 0.8. I have a mg cosine theta, and it has a lever arm of this distance right here, which is this distance right here is 1.5. And that's also positive. In other words, those are both trying to rotate in this direction. The sine is trying to rotate in this direction. The cosine is trying to rotate in this direction about that point. Let's look at the tractor itself. It has this mg sine theta, and this is the lever arm right there. Looks like that's the lever arm right there is 0.5. So plus mg sine theta times the lever arm of 0.5. The only one going backwards is mg cosine theta times its lever arm. This is again the tractor. it has this lever arm right here, 0.75. Actually, it's 0.75 minus 0.15. So it's 0.75 between the tires, but 0.15 is the distance here. So this would be a total distance of 0.6. So there's 0.6. That's equal to 0. So again, these are for this is the loader, and this is for the stone. Okay. Once you do that, just start plugging numbers in. See if I can move that up just a little bit. So here I have 300 is the stone, 300 times 9.81. Then I got sine theta times 0.8 plus cosine theta times 1.5 plus, in this case, I didn't talk about that, but the loader has a mass of 1180. So that'd be plus 1180 times 9.81. And that's going to be sine theta times 0.5 minus cosine theta times 0.6. That's all equal to 0. Do some arithmetic, and you can see that theta here is equal to 17.3 degrees. Okay, there you go. Those are the ways I would suggest you attempt to solve for some of these more advanced inclined plane problems.